Adding and subtracting rational expressions. We know a rational expression is a ratio of two polynomials. So let's first look at the most simplified version of that scenario, which would just be a single constant term up top and a constant term on the bottom. In this scenario, you are likely familiar with from previous years. So say we have 1/4 plus 3/4. So here we have two rational expressions that we're trying to add together. And we know that through addition subtraction, we need common denominators. That is already taken care of for us. So what essentially we're asking is how many fourths do we have in total, right? So there's 1/4 and another 3/4 for a total of 4/4. And at the end, once we combine those through addition or subtraction, we can look to simplify that final answer to, in this case, get 1. In the event that we have uncommon denominators, how do we get the common denominator so that we are able to, in fact, add or subtract these values? The most efficient way is identifying what the least common multiple is. And the reason why we want to look at the least common multiple, and I'm referencing the denominators here, is because when the expressions get more complex, it will be the most efficient pathway. So how do you identify a least common multiple? Well, look at the two denominators in question, 6 and 9. And the first thing you want to do is write their factorizations. So 6 could be expressed as 2 times 3. And 9 is 3 times 3. So they're factorizations, and I should say they're prime factorizations. Then we want to look at these factorizations, and any repeated factors we want to express in an exponent form. So 3 times 3 is equivalent to 3 squared, and we can't do anything with 2 times 3. To identify the least common multiple, we compare the factorizations. So upon comparison, we look to identify uncommon and common factors. Any uncommon factors must be included in the least common multiple. So when I compare the two factorizations, I notice one of them has a 2 and the other doesn't. So I would consider that uncommon, and therefore it must be included. Then I look at the 3, and I would consider that a common factor. Once I've identified a common factor, you select the one with the higher power, which in this case is 3 squared. And when simplifying this, 2 times 3 squared is 18. Now that is the value you could probably come up with mentally without going through that process. But again, it's good to understand how to get a least common multiple as the things get more complex. Now that we've identified the common denominator being 18, we then ask ourselves, if I'm going to go from 6 to 18, I need to make sure I adjust the numerator the same way. Okay, so going from 6 to 18 requires multiplication times 3, and therefore I must multiply the top by 3 as well. So by multiplying the bottom by 3 and the top by 3, the ratio of those two values together equals 1. And multiplication by 1, we know doesn't change the value of the expression, but rather just how it looks. And that's ultimately what we're trying to do. We're trying to identify a way to group the 6 and 9 into a common format so that we can identify how many 18ths do we have in total. So adjusting the numerator, we'll go from 1 to 3, and we know 1/6 and 3/18 are equivalent. How do you get from 9 to 18? You multiply by 2, so the top must be multiplied by 2. So in total, how many 18ths do we have? 5 over 18. Okay. Now that may have seemed overly simplified to begin this video, but as you will see, when things get more complicated, it's a good process to know. So now we have these monomial expressions with the introduction of variables, and we want to add these together. To add them, we must get common denominators. So let's first identify the least common multiple between our denominators. So we have 8x to the 4th, y, and 12xy cubed. For the number, we can write its prime factorization. It's going to be 2 times 2 times 2, and we said repeated factors we want to express through its exponent format, so 2 to the 3rd. Now x to the 4th, we could break that down into x times x times x times x, but we're just going to have to group it back to x to the 4th anyway. So we can keep the variables as is in this scenario. Now breaking down 12, that's going to be 2 times 2 times 3. So 3 times 2 squared. Now when taking the least common multiple, what are the uncommon factors? So both of these factorizations, right? So now we're comparing the factorizations. They both have 2's, x's, and y's. So the only thing not shared is the 3. So that must be included. Uncommon factors must be included in the least common multiple. Then when I look at the common factors, I take the one with the higher power. So comparing 2 cubed and 2 squared, we're going to get 2 cubed. X to the 4th and x, I'm going to take x to the 4th. And y cubed, I'm going to take y cubed. We can simplify this. 2 cubed is 8 times 3 is 24. X to the 4th, y cubed. So there's my common denominator. So now I'm going to rewrite this problem with that common denominator so that I'm able to add these together. Now you'll see that both denominators got adjusted to this new common denominator. So we must adjust the numerator the same way. So how do I get from 8x to the 4th y to 24x to the 4th y cubed? We can see that we had to multiply the numeric value by 3. So maybe I'll write a dot for multiplication. So multiply by 3. The x stayed the same, and the y went from y to y cubed, so I have to multiply by y squared. So we must have to also multiply the top by 3y squared, which was going to result in 9y squared. Now let's look at the second expression. We have to multiply by 2 for the number, x to the 3rd for the x, and then didn't have to adjust the y. So let's do the same here. We have to multiply by 2x cubed, so 1 times 2x cubed is 2x cubed. Now we can add these together. And we'll get 9y squared. So these are not like terms, so I can't combine them. So add the numerators, keep the denominator. And what I could do from here, again, when we get our final result, look to simplify. So can I simplify this any further? There's no common factor in the numerator to remove in hopes of a cancellation. So this is the best I can do. Now let's jump over to examples that have polynomials in the denominator, so multiple terms. So we just looked at one that introduced variables, but there was only a single term in the denominator. So first recommendation for you is anytime you're given multiple terms in the denominators, your first step in an addition subtraction problem should be to factor the denominators. You do not care about factoring the numerator because ultimately you're going to be looking to combine like terms anyway through the sum or difference process. So factoring is actually going to be counterproductive in that sense. So bottom left is a difference of squares. Bottom right is just linear, can't be factored, there's no GCF to remove. Now when I compare these two, these are the fully factored forms, so I can identify a least common multiple. What's common amongst them and what's uncommon? So what's uncommon must be included, the x plus 4. What is common is x minus 4. So there's your common denominator. So now we can adjust the denominators so that we have them both over x plus 4, x minus 4. Now to get from the first denominator, so this first expression's denominator, to the new denominator, well, we didn't have to adjust anything because that first denominator was in fact the common denominator. The second denominator, x minus 4, was adjusted. We had to multiply by x plus 4. So remember, we must also do that to the top to make sure we're multiplying, we're scaling by a form of 1. Now, we have our common denominators. So we know we're going to keep that. Now, how do we combine that numerator? Well, we're going to ultimately want to distribute this so we can properly identify like terms. So we're going to have 3x plus 12. Now, here's the catch. With subtraction, we have to make sure we're paying attention to the fact that we have to subtract the entire numerator expression. So minus 3x plus 12. So if you have to write this step, that is suggested. Distribute the negative. Now we can combine like terms. Okay, then once we get our final result, look to simplify further. So we're going to say, well, we can take out a -1 from the top, and we're going to get x plus 4. And that will allow us to cancel with that x plus 4 on the bottom to get a fully simplified answer of -1 over x minus 4. So here is the difference between those two original expressions that did not have common denominators. So we found the common denominator. We made adjustments to numerators where necessary. Then this was a subtraction problem, so we had to make sure we identified that we were subtracting the entire numerator of the second expression. So distribute the negative, then combine like terms, and look to simplify at the end. Now, before we move on to the next example, you may be asked to find values for which the expression is undefined. When doing that, we're looking for values that make the denominator 0, right? Because dividing by 0 is undefined. So how do we identify that? We're going to look at our original denominators and solve those to identify the values for which the expression is undefined. So solving the quadratic in this case requires a factorization here. So we're going to look at these original denominators to identify values for which the expression is undefined. And in this case, we're going to get x cannot equal 4 or -4 from your solutions. You can see from this factored form in the step below, that will support that. Now, the reason why you want to look at the original denominators is because you don't want to forget about any values that would cause that to happen, which can occur if you consider after cancellation. So you'll see in this step here, we canceled out the x plus 4s, and that x plus 4 in the denominator was responsible for the identification of -4 being as excluded value. So always check original denominators to answer that question, not the fully simplified version, because you might miss out on some values. Next example, subtraction again. In this case, both denominators are already fully factored. Again, addition subtraction problems, we're only looking to factor the denominators. We don't want to do the numerators. Again, counterproductive, because ultimately we want to combine like terms. So when I'm identifying least common multiple between these two, they're already factored. So looking at the factorizations, what's uncommon? Well, one has an x plus 2, the other doesn't, so that's included. And one has a 3x minus 1, the other doesn't, so that's included. There's nothing common. So now let's adjust. You can see to go from x plus 2 to this new common denominator require the multiplication of 3x minus 1. So we must also multiply the top by 3x minus 1. Same idea for the second one. 3x minus 1 to x plus 2 times 3x minus 1. So we must also multiply the top by x plus 2 to stay consistent with the idea that we're multiplying by a form of 1. Now, because we want to combine like terms and ultimately find the difference, we're going to want to make these distributions here. So there's a double distribution in the first example. We're going to have 9x squared. So minus 3x minus 6x is minus 9x plus 2. And over here, we're going to have 2x squared plus 4x. So we have 9x squared minus 9x plus 2. And remember, we're subtracting the entire numerator over here. Now distribute. And combine like terms. And then let's look to simplify our final answer. So could we factor this numerator any further? So we're saying 7 times 2 is 14. Are there any two numbers that multiply to 14 but add to -11? And the answer is no. So there's no combination there. That means the top can't be factored any further. There's no GCF to remove. There's no cancellations to be had. So this is the final result. and values for which the expression is undefined. We're going to check our original denominators. The original denominators produce x cannot equal -2. That would make that first one, and then x cannot equal 1/3 as a result of solving those two denominators to find the zeros. That's what x cannot equal, right? Because we're looking to figure out what numbers would result in the denominator equaling 0. So there are your two values for which the expression would be undefined as a result. And last one. So a couple quadratics here. By now we know we have to factor this thing to properly identify a common denominator. In these quadratics, what multiplies to -20 adds to negative. We're going to x minus 5, x plus 4. And over here, we're going to have x minus 5, x minus 3. So there are full factorizations. So now we can identify a least common multiple between them. So shared and unshared. Well, what's not shared is x minus 3 is in one of them, but not the other. X plus 4 is in one of them, but not the other. And x minus 5 is shared, so take the one with the higher power. So there's your common denominator. So let's adjust accordingly. We're going to have x minus 5, x plus 4. And to get from that original to the new common denominator, we have to tack on an x minus 3, which means we must adjust the top with the same, in the same way. So multiply by x minus 3. And then plus, oh sorry, there should be a 2 here. We originally had x minus 5, x minus 3. We have to introduce an x plus 4 to get that common denominator, so multiply the top by x plus 4 as well. Distribute, so we're going to get 5x minus 15, and then we're going to get 2x plus 8. And this is an addition problem, so we don't have to worry about distributing it negative or anything. It's just a matter of combining like terms. So we're going to have 7x minus 7. We're going to have x minus 5, x plus 4, x minus 3. We could look to simplify this further. We could take out a 7 up top, which would leave behind x minus 1, but unfortunately that doesn't cancel out with anything on the bottom. So factoring out the 7 doesn't make anything more simplified for us. So therefore, that's the best we can do in identifying values for which the expression is undefined. We're going to check original denominators. We can solve these through factorizations, which we did in the second step. So solving those, we find out that x could not equal 5, -4, or +3 if we wanted a defined expression. So there's the general approach to addition-subtraction. If you have common denominators already, you are ready to go. You're just going to add or subtract numerators and keep denominators. If you don't have common denominators, your goal is to identify the least common multiple between them to advance in the most efficient way towards your final answer. And to identify least common multiples requires a full factorization of the denominators because we compare the factorizations when identifying LCMs. What's uncommon must be included. What's common, you take the one with the higher power. And once you identify the common denominator, make sure you can then identify from there what adjustments need to be made from the original denominator for that portion of the expression to the new common denominator and adjust the numerators in the same way. Okay, super important that we're also adjusting numerators. Then combine like terms as you normally would with polynomials. And the other thing with subtraction, make sure you're distributing the negative to the second numerator to showcase that we are indeed subtracting that entire expression, not just the initial term. And once you get your final result, always look to simplify further if possible. And that is a video on adding and subtracting rational expressions.